Torque can be defined as the moment exerted on a member in an attempt to twist it about its longitudinal axis. The effect it takes becomes a primary concern while designing graph plots, which are found in automobile and machineries. On the right hand side, you can see there is an example of a styrofoam tube in which there are boxes drawn. The left side box is a rhombus and the right side box is a rectangle. Now, when we apply a torque on this styrofoam tube, by torque I mean the right hand goes upwards or twists the tube upwards and the left hand twists the tube downwards. By doing this, we can see there is a change in the shape of these boxes. The rhombus here has a change in its length and breadth. At the same time, the rectangle here has a change in its angles. So by change in angle, it means that this rectangle is undergoing shear stress while the rhombus is undergoing normal stress. But this is exactly opposite when it comes to the previous example which we saw in our previous session, which was the elongation of the glove. In the elongation of the surgical glove, we saw that the rhombus was experiencing shear stress and the rectangle was experiencing axial stress or normal stress. Now these are the effects of applying torque to a tube. A more digital illustration can be given by considering a shaft made of another material that is highly deformable. Example, rubber. The grid lines that run longitudinally, which are inscribed on the shaft, tend to distort with the application of torque. The distortion often takes the shape of a helix that can be observed to intersect the circular section at equal angles. Additionally, the cross sections of the shaft are assumed to be constant and do not experience any form of bulging or warping. Now, we can easily see the difference between the parallel lines that are running here before deformation and the parallel lines that are intersecting with the neutral axis of the cross section. We have already come across this concept called neutral axis when we were studying about bending and deflection. The neutral axis works the same way here, where it is not changed with whatever torque is given. We also should note that there is a unique distinction for the radial lines. The radial lines can also be seen to remain straight, where rotation can be observed with the deformation due to the applied load. But one more thing which we have to note here is when the twist angle is quite small, the length and the shaft radius can be assumed to be practically unchanged. Next, we'll see what is torsion formula. A shaft which is made of cross section in the form of a circle experiences twisting on applying torque in a way that the shaft's shear strain always remains proportional to its radial distance from the center. This basically means that the increase in the radial distance will result in further increase in the shear strain of a shaft. So therefore, at the highest radial distance, which is the radius of the shaft, the strain is highest, or you can say that the stress is highest. Now here, assuming that the material has linear elasticity and is homogeneous, the torsion formula that can be used to calculate the shear stress is tau max, which is equal to TR by J. Here, tau max is the maximum shear stress in the shaft occurring, which is always on the outer surface. Now, if we substitute rho in place of R, it means that the shear stress that is happening at any point rho from the center of the shaft or the neutral axis of the shaft. This distance can also be given as rho. But we have to note here that when rho is equal to R, we again get the value for maximum shear stress. Now we can see the formula here, and in this formula T is the resultant internal torque acting at the cross section, whose value can be easily determined from the torque diagram. Next, J is the polar moment of inertia, which can also be called as the section property of the given material. R is the outer radius of the shaft, and rho can be the intermediate distance on the cross section. So basically rho can vary from 0 to R. Some of the common places where we can observe torque are creation of torque in machineries and motors which has twist in them. So basically we know that motors have twist in them, and some other examples are drive shafts, wrenches, seesaws, and other places. So we can see that a wrench is tightening a bolt here, and obviously torque is involved here because there is twisting motion. In the next diagram, we can see that a seesaw that is having a twisting motion which is fixed at the center. It's kind of rotating about the center, but it's not extremely high rotation. So there will always be an internal torque to balance the rotation at the center. And then next we have a pulley system that is again a control using torque. Next, let us see what shear stress is. Torsional shear stress develops when transmitting a torque from one plane to another. For example, a shaft connecting an electric motor to a pump. Now, the main assumptions is that the stress concentrations at connecting devices can be ignored. Now, the assumption means that if we have a motor which is connected to two shafts at the end, then the shear stress that is experienced on the motor or stress concentrations that is experienced on the motor due to the connections can be ignored. But other than that, we'll be finding the shear stress that is acting on the motor. Now, for equilibrium, if a torque T is applied at one end of the shaft, every cross section must resist the torque. This resistance is basically the reaction force or the reaction torque that is happening against the torque which is applied. This reaction torque can be given as TR, and it is caused by the shear stress distribution across the cross section. Now, if we take the diagram in the right side, at any radial distance rho, the shear stress is constant. However, as the value of rho increases or decreases, the value of shear stress also increase and decrease. So it's basically proportional to the value of rho. Coming to the force dF, we know that force is equal to stress into area. So dF will be equal to tau rho into dA, where tau rho is the shear stress that is acting per meter, that is acting per meter square on the distance rho. Now dTr will be equal to rho dF, because we know that moment is equal to distance into the force applied. Now we know the value of dF, which is tau rho dA. So we can simplify that value here and we'll get dTr is equal to tau rho dA. Taking integration both sides, we'll get the value of Tr, which is equal to tau rho dA. Next, the same way we can calculate torsional shear strain. From the previous sessions, we know that stress is equal to multiplication of modulus and strain. Here, again we can see that tau C, which is shear stress, is equal to G into gamma C, which is the shear strain. Now G here is the shear modulus, while C here denotes the maximum radial length from the center. Rho denotes the point anywhere inside the radial length. So basically the shear strain at a distance rho from the axis. We know that strain can also be given as change in length by length. Now here again, gamma C, which is actually tan gamma C, is equal to del B divided by the actual length. But for small angles, tan can be negated and gamma C is equal to del B by L. And again, inside the material at a distance rho from the axis, gamma rho is equal to del rho by L. Now for the angle of rotation, which is theta, we know that for the distance C, it is del B by C, and for distance rho, we know that it's del rho by rho. Dividing L in all these equations, we get the formula gamma C by C, which is equal to gamma rho by rho, which is basically after simplifying L here. Now we know that gamma C is equal to del B by L, and the same way gamma rho is del rho by L. And we are substituting these equations. Here we get a relation between gamma rho and rho. This means that for every increase in the value of rho, there is a linear increase in the value of gamma rho too. Now that we got the relation between rho and gamma rho, we'll go into finding the elastic torsion formula. But before finding the elastic torsion formula, we need to address some assumptions. The first one is that the shaft that is undergoing a torque is circular. It has a constant cross section. The value of strain and the value of angle is small. Finally, shear stress and strain have a linear relationship, which is it falls under the proportionality limit. Now for the elastic torsion formula, from the previous slides we know that tau rho is equal to G into gamma rho, and same way tau C is equal to G into gamma C. Substituting these formulas into the relation which we got, we get tau rho by rho is equal to tau C by C. Therefore, again we can say that tau rho is equal to tau C by C into rho. Now, if we recall the formula for torque, which is T equal to integral of tau rho dA, we can substitute the value of tau rho which we found now into this torque formula, and finally we get a simplified version which is T is equal to tau C by C and integral of rho square dA. Here, the integral of rho square dA can also be called as polar moment of inertia. Now for maximum torque, we take the maximum value of shear stress, which is tau C max, and the maximum radial distance, which is C. At the same time, the same formula can also be possible for a distance rho from the center point inside the surface of the shaft. So tau C will be equal to T into C divided by J, and tau rho will be equal to T into rho divided by J. Next, let us see what polar moment of inertia is. Now, polar moment of inertia can change for a solid shaft and a hollow shaft. We know that J is the polar moment of inertia, and in a shaft with a circular cross section where the thickness of the ring is dou rho and the circumference is 2 pi rho, for this ring we can say that area of the ring is equal to 2 pi, which is 2 pi rho, which is the circumference, into dou rho, which is the thickness. To calculate J for this shaft, from the previous slide we know that J is equal to integration of rho square dA. Now taking the area integration of rho square dA and giving it limits 0 to r, if we substitute the value of dA in this equation, we get 2 pi integration of 0 to r dou cube d rho. Now taking the limits, as for a solid section, we'll get J equal to pi by 2 into r to the power 4 after simplifying the integral. And the same way for hollow tubes which has inner radius Ri and outer radius Ro, after simplifying the integration we get J equal to pi by 2 into Ro to the power 4 minus Ri to the power 4. Now when we come to shear stress distribution, shear is same on adjacent surfaces which we saw. So by using the formula for torsion, we need to address the sign convention that goes with the shear stress distribution. We previously saw sign convention when we were working on SFD, BMD and deflection. Now we'll see sign convention for torsion formula. Again, when we use the right hand thumb, when we take a shaft, in the right side and the left side region of a shaft, if the reaction is acting outwards, then the torque is positive. The same way, if the reaction is acting inside the shaft, then the sign convention is negative there. Next, we come to the analysis procedure. The torsion formula can be applied on any material system, and for any material system, this procedure should be followed to find the desired values. The first step would be to address the internal torque. The shaft should be sectioned at a point perpendicular to the axis to calculate shear stress. Now to calculate the internal torque, we need to take free body diagrams and equilibrium equations. And we move on to the second step, which is section property. Basically, section property is the polar moment of inertia. We already calculated different polar moment of inertia for different type of shafts, and we'll use the exact same equations to calculate the polar moment of inertia for a given cross-sectional area. The next step would be to calculate the shear stress. The radial distance rho should be specified, which is measured from the center of the cross-section to the point at which the shear stress will be calculated. Once the distance is specified, the torsional formula should be applied and the unit should be kept consistent. Now, with this torsion formula, we can find different values. We can find the torque, we can find shear stress, and more. But one thing to note here is that shear stress is assumed to always act on the cross section along the direction which is perpendicular to rho. The force created by the stress contributes to the respective torque about the shaft's axis, which has the same direction as that of the internal resultant torque T acting on the section. So this actually means that the direction of the torque created due to force is same as that of the internal resultant torque acting on the section. With that, we'll move on to solving a problem, a very simple problem, wherein we find torque, shear stress, and etc. of a shaft. Here we are given two shafts, one is a solid shaft and the other is a hollow shaft. In the problem, the allowable shear stress of the solid and hollow shaft shown is 75 megapascal, which is the maximum shear stress. We are supposed to determine the maximum applicable torque for each cross section and determine the stresses acting at point A on the solid shaft and at point B and C for the hollow one. Now, we cannot do the first step from the analysis procedure because here we don't have any means for the free body diagram or equilibrium forces. Instead, we can go for the second step, which is the section properties. Section properties that can also be called as polar moment of inertia. So each shaft, the solid shaft and the hollow shaft, have different polar moment of inertias. Here Js is equal to pi by 2 r to the power 4 from the formula, and the same way for hollow shaft it is pi by 2 into r o to the power 4 minus r I to the power 4. The polar moment of inertia for solid shaft, after simplifying the values which we know in the formula, is 0.1571 into 10 to the power minus 3 meter power 4. Here 0.1 is basically 100 mm changed to 0.1 meter or converted to 0.1 meter. Same way, for hollow shaft, we can see that the outer surface is 0.1 to the power 4 minus the inner surface, which is 0.075 to the power 4. With that, we move on to the first problem, which is calculating the maximum torque. Formula for shear stress is tau max is equal to Tc by J. Here, we need to find the maximum torque for the solid shaft and maximum torque for the hollow shaft. Ts is given as the torque for solid shaft. From the formula, tau max is 75 into 10 to the power 6, which is 75 megapascal. And if we substitute values of distance, which is radial distance, and polar moment of inertia for the solid shaft in this formula, we get the torque of the solid shaft, which is 118 kilonewton meter. Similarly, if we substitute the associated values with the hollow shaft, we get TT, which is equal to 80.5 kilonewton meter. Now, we need to keep in mind that kilonewton meter is the unit of torque. From the problem given, the next statement was for us to determine the stresses acting on different points A, B and C in the shaft. If we see this diagram, point A and point B in the solid and hollow shaft respectively are located in the outermost surface, and we know that the outermost surface is experiencing a maximum shear stress of 75 megapascal. Therefore, point A and point B are also experiencing stress of 75 megapascal. However, we need to find the shear stress that is experienced by point C. For point C, tau I will be equal to Tc by J. Tau I is the stress that is experienced in the inner circle of the shaft. We know the torque of the hollow shaft. We also know the distance, the radial distance from the center point for the inner circle. The inner circle distance is 75 mm and we have converted it into 0.075 meter divided by J. J is the polar moment of inertia of the hollow shaft. From that, we get the shear stress experienced in the inner circle, which is 56.2 megapascal. Now, this can be the same as the shear stress that is experienced by the point C. With that, we come to the end of this session. So, to summarize this session, in this week, we learned about beams and their properties. We also saw beams as versatile structural elements. We saw some of the examples of beams and supports for beams. Then we came across loads acting on a beam, and we also saw problems that are relating to bending moment diagrams and shear force diagrams. Later, we learned about the concept of bending. We also saw the concept of deflection. We came across various formulas related to bending and deflection. Finally, in the last section, we saw what is torsion and torsion on a circular shaft. We came across torsional formula, derived it, and also worked on a problem that is related to torsional formula. That's it for this week. See you in the next week. Thank you.